Welcome to AI Peer Review. Today we're diving deep into an interesting paper that presents a really compelling approach towards building AI systems that don't just process information, but truly understand and interact with the physical world around us.
Yeah, the fundamental idea they're exploring is uh, deeply inspired by human cognition.
Hmm.
Think about how you learned about physics, not by being fed equations or instructions, but by watching, right?
Yeah.
By observing how objects move, how things fall, how forces interact.
Mm-hmm.
You build this internal model of the world just from that observation,
Hmm.
and then you use that model to predict what's going to happen next, or maybe plan your own actions. This work is really about giving machines that same kind of fundamental capability.
Exactly. And the paper introduces a system they call V-JEPA 2, which is a significantly scaled up version of something called a joint embedding predictive architecture.
Right.
They also present V-JEPA 2 AC, where the AC stands for action conditioned, meaning they've adapted this observational model to understand how actions influence the world, specifically for, well, robotic control.
So over the next little while, we're going to unpack how they approached this, the self-supervised pre-training that lets the model learn from watching just massive amounts of video, the specific technical innovations that allowed them to scale it up so effectively.
Yeah, the scaling is key here.
Definitely. And then how they took that purely observational understanding and adapted it for action and planning. And finally, we'll look at its performance across a whole range of tasks. Stuff like basic video understanding, predicting human actions, all the way to controlling actual robots in the real world.
Our mission in this deep dive is to really pull out the core insights, find those aha moments, and understand what this could potentially mean for the future of embodied AI, machines that can learn, think, and act within our physical reality.
It's pretty exciting stuff.
Okay, so let's unpack this core challenge. The problem they're grappling with is pretty profound.
Yeah.
How do we create artificial agents that learn a world model directly from raw sensory data, like, say, streaming video from a camera? We want systems that can look at a scene, intuitively grasp the underlying dynamics, predict future states based on those dynamics, and then use that predictive capability to plan actions to achieve a goal. It's the difference between an AI that can recognize objects in a photo and one that can actually navigate a cluttered kitchen to find and pick up a specific mug.
Right. And the traditional ways we've trained robots or embodied agents often rely really heavily on lots of specific interaction data. You might teleoperate a robot, or you set up experiments with clear success-failure signals, reward functions.
Yes, the classic RL setup.
Exactly.
Mm.
And that's effective for narrow tasks, but getting the sheer volume of high-quality, diverse interaction data needed to train truly generalist agents, it's incredibly difficult and expensive. You can't just scrape billions of hours of perfect robot task data off the internet like you can, say, cat videos.
Good point. And while recent research has started tapping into that huge pool of internet-scale video, many approaches focus on generative modeling. Their goal seems to be predicting and generating future video frames that look visually convincing, at a pixel level.
And they can look amazing, visually very impressive. But the paper points out a critical limitation here. These pixel predictive models often waste a lot of capacity trying to accurately predict every tiny, unpredictable detail, like the exact way a leaf flutters in the wind or the specific pattern of ripples on water.
Things that don't really matter for the core dynamics.
Precisely. For planning, you don't need to predict the exact pixel color of every leaf. You need to predict the important dynamics, like whether a falling object will land on the table or maybe hit the floor.
Okay, so this is where their approach gets really interesting, and it's central to this V-JEPA architecture. They build on the self-supervised learning hypothesis.
Right, the idea that you can learn incredibly rich representations of data just by finding patterns and making predictions within the data itself, no explicit human labels needed.
And specifically, they use the Joint Embedding Predictive Architecture, or JEPA.
Yeah, GP. And the core GP idea is actually a really clever pivot. Instead of predicting pixels, you predict in a learned representation space.
Okay, let's dig into that distinction because it feels really key. Why is predicting in a learned representation space so much more powerful or maybe more suitable for learning dynamics compared to predicting raw pixels?
Well, think of it like this. Pixels are the raw sensory input, right? They're full of noise, irrelevant detail, just everything. Predicting every single pixel forces the model to get distracted by all that stuff.
Like that fluttering leaf example.
Exactly. If that leaf twitches unpredictably, a pixel-level loss function will actually penalize the model for not predicting that twitch perfectly. But if the model first compresses the video into a more meaningful representation, let's imagine this representation captures things like object identities, positions, velocities, maybe scene structure.
Higher level concepts.
Right. Then it can predict the representation of the next state, that unpredictable leaf twitch. It might simply be ignored or filtered out in that representation space, while the predictable trajectory of, say, a ball being thrown is captured and accurately predicted.
So the representation space itself acts like a filter. It lets the model focus on the core dynamics, the predictable structure, while hopefully discarding the noise.
That's the idea.
Yeah.
And because this representation space is learned by the model during training, the model can tailor it to capture exactly those aspects of the world that are stable and predictive over time.
Makes sense.
And this is why self-supervised learning is such a powerful match for JEPA. By making these predictions within this learned, filtered space, purely from watching massive amounts of internet video without needing explicit labels or paired actions, the model can learn incredibly powerful video representations and an implicit predictive model of how the world evolves. But it's evolving in this abstract, predictable space. That's the fundamental capability V-JEPA 2 is built on.
All right, so they have this elegant idea. How do you actually take that and make it work at, the massive scale required? This paper details how they turned the original V-JEPA into the much larger and more capable V-JEPA 2. The core objective, if you visualize it, maybe thinking about figure 2 in the paper, the left side.
Right.
It involves taking a view of a video where some parts are masked out. Think of it like just blocking out chunks of frames. And the model's job is to predict the representation of the original unmasked video, but only for those areas it couldn't see.
Exactly. You've got an encoder that processes the visible parts and extracts a representation. Then there's a predictor that takes that representation and tries to essentially fill in the missing pieces. But again, crucially, not by generating pixels, but by generating the representation of those missing pieces.
And they're trained together.
They're trained together. The training signal, the loss function, focuses only on how wide the predictor's output matches the actual representation of the masked areas.
Right.
And to prevent a sort of trivial solution where the model just learns to ignore the input and predict, the average representation or something.
Oh, yeah, collapse.
Right, collapse. They use a few standard tricks from self-supervised learning. Things like stopping the gradient on the target representation so the predictor's chasing a stable target, and using an exponential moving average, or EMA, of the encoder's weights to provide that stable target.
Got it. So the encoder's learning to create good representations, and the predictor's learning to leverage those representations to foresee the masked out parts, maybe the future, and the technical architecture underneath.
Well, both the encoder and the predictor are based on vision transformers, VITs, which have been, incredibly successful in image and video tasks lately.
Standard workhorse now.
Pretty much. And for handling the video structure, space and time, they used a clever adaptation of a technique called rotary position embedding, or ROPE.
Okay.
So instead of the standard ways models figure out where each piece of video comes from, they extended ROPE into 3D rope. So it handles the temporal axis, the height axis, and the width axis simultaneously. They found this really helped stabilize training, especially as they scaled the model size up significantly.
Right, which they definitely did. And the videos themselves, how are they processed?
They're processed in small spatiotemporal chunks they call tubelets. Think like 2 frames deep, 16 pixels high, 16 pixels wide. And they use a strategy called multi-block masking to decide which of these tubelets get hidden from the model during training.
Okay, so what were the specific ingredients that allowed them to scale V-JEPA from its initial version up to V-JEPA 2? They highlight, I think, 4 key factors in Section 2.1.
Yeah, 4 main things. First, a massive increase in data scale. They went from a data set around 2 million videos, which is already pretty big, to a huge collection of 22 million videos. That's, over 10 times the amount of observational data?
Huge jump. Second,
model scaling. They significantly increased the size of the neural network itself. The encoder grew from a roughly 300 million parameter VITL model.
VITL.
Right, VIT large, to an over 1 billion parameter VITG model. That's a massive jump in the model's raw capacity to learn complex patterns.
Okay, data model size. Third,
longer training. They just trained the model for much longer. They extended the training schedule from around 90,000 steps to 252,000 steps. They used a specific learning rate schedule warm-up, then constant, then decay, which they found cost-effective for these very long training runs.
Makes sense for large models. And the fourth factor,
higher resolution processing.
Yeah.
But they did this cleverly. Instead of training at a high spatial resolution or with long video clips right from the start, which is computationally very expensive,
Immensely.
right? They used a progressive strategy. They trained initially on lower spatial resolutions, like 256 pixels, and shorter video clips, maybe 16 frames. Then, gradually, during the later stages of training, they increased the resolution, say to 384 pixels, and the duration up to 64 frames.
And you can really see the impact of these ingredients when you look at their results, like in Figure 3 of the paper.
Absolutely. Just increasing the data from 2 million to 22 million videos gave them a noticeable performance boost, about 1 point on average across 6 different classification tasks. It particularly helped on tasks that rely more on appearance, like recognizing objects and scenes in Kinetics 400 or ImageNet.
But the single biggest factor seemed to be the model scaling.
That's right. Simply moving from the smaller VITL to the larger 1 billion parameter VITG added another even larger jump, about 1.5 points average gain on top of the data gains. That model capacity really mattered.
And then the longer training added more.
Yep, longer training provided further improvements, another 0.8 points or so. And finally, incorporating that progressive higher resolution and longer video duration training pushed the overall average accuracy up even higher, to around 88.2%. It's a really clear demonstration that you need to scale across multiple dimensions, data, model size, training time, and input fidelity to unlock this level of capability.
They also talk quite a bit about data curation, especially in the appendix, section 8.2. They didn't just use any 22 million videos, did they?
No, and this is important. They started with a massive source, YT1B, that's about 1 billion videos from YouTube. But they applied a clever filtering process. They extracted distinct scenes from these videos and then clustered them based on visual similarity, using features from another powerful vision model, Dino V2.
Okay, so grouping similar scenes together.
Exactly. And the key step was they only kept clusters that seemed relevant to their target distribution, filtering out maybe irrelevant content or noise. This resulted in a curated dataset they called Curated YT1B.
And training with this curated data made a difference. They show this in Figure 4, right?
It did. Training with this curated dataset compared to using the same volume of uncurated data from YT1B gave them a solid 1.4-point average improvement on their benchmarks. It really highlights that the quality and relevance of the data in your vast dataset matter, not just the raw quantity.
That makes intuitive sense.
And what's particularly interesting, they mentioned this in relation to Figure 12, I think, is that for very long training runs, the model trained on the uncurated data actually started to degrade in performance after a certain point.
Oh, interesting. Performance went down.
Yeah, slightly. Whereas the model trained with the curated data continued to improve or at least stayed stable. It suggests the curation process might have filtered out noise or potentially misleading information that could eventually confuse the model if it just kept training on it indefinitely.
Like trying to learn a consistent rule from really noisy examples, eventually the noise starts to hurt more than help. And speaking of efficiency, that progressive training strategy for resolution and duration seems quite smart.
Absolutely. When you look at how they schedule the training, as shown in Figure 5, they only incur the heavy computational cost of processing those longer, higher-resolution video clips in the final phase, what they call the cooldown.
So most of the training is chipper.
Exactly. They report that this approach effectively reduced the required GPU time for achieving that final high-resolution performance by over 8 times compared to if they had tried to train at full resolution and duration from the very beginning. It's one of those critical details that actually makes scaling like this practical.
Okay, so they've built this really powerful V-JEPA 2 model.
Yeah.
It's learned rich visual representations. It's captured a sense of world dynamics just by watching mountains of video. But as you mentioned earlier, watching is different from doing. How do they take this observational understanding and translate it into the ability to actually control a robot?
Right. That's the crucial next step, and that's where V-JEPA2AC comes in the action condition version. The core idea here is once V-JEPA2 is pre-trained, its main visual encoder is frozen.
So its weights don't change anymore.
Exactly. It's like having this highly knowledgeable visual system that understands the world's physics implicitly, baked in from all that video. Then, they train a separate action condition predictor on top of this frozen encoder. This new predictor module is specifically trained to understand how actions change those learned representations of the world.
Okay, and crucially, this is where they finally introduce interaction data, actual video of a robot performing tasks. But the paper highlights they needed only a small amount of this data. relatively speaking.
Yeah, that's a really key point in Section 3. They use data from the droid dataset, which is video footage of a Frankopanda robot arm being teleoperated. The total amount of video they used for this action conditioning phase was under 62 hours.
62 hours, that's tiny compared to the millions of hours for the initial pre-training.
Tiny. And it's also relatively small compared to the datasets used in some other robot learning approaches that rely heavily on imitation learning from expert demonstrations.
So what kind of data actually goes into training this action condition predictor? What's the input?
Okay, so for each step in the robot video, the input includes a few things. You've got the video frame itself, XK. You've got the robot state, ABS-K, which is usually its end effector, position, and orientation, plus maybe gripper status, represented as like a 7-dimensional vector. And critically, you have the action taken between that frame and the next, also often a 7D vector, representing the change in the robot state.
So where it is and what it just did.
Exactly. These AKXK, where CK is the visual feature, are sort of temporally interleaved and fed to the predictor. The frames are first encoded independently by that powerful frozen V-JEPA2 encoder to get those rich feature maps CDK we talked about. These maps have a shape like, say, 16 by 16 by 1408 for the big VITG encoder.
And the goal of training this new predictor, what's the loss function optimizing for?
The predictor is trained to take the current state representation in CK and the action, AK, and predict the representation of the next state, +1. The loss function measures how close its prediction is to the actual representation of the next state, CK+1, again using the frozen V-JEPA2 encoder to generate that target representation. The power comes from leveraging the encoder's deep, observationally learned understanding. The predictor only needs to learn the function that maps actions to changes within that pre-existing understanding.
And the predictor itself is another transformer network, right? About 300 million parameters, I think?
Correct. It's a reasonably sized transformer, around 300 meter parameters. It takes the action vector, the state vector, and the flattened visual features from the encoder, projects them all into a common format, and then processes them. It uses that same 3D rope for the visual patches and a simpler temporal rope for the action and state tokens to keep track of where everything is in sequence.
And it has a specific attention pattern.
Yeah, it employs what they call a block causal attention pattern. This basically ensures causality when it's predicting frame K+1. It can only look at information from frame K, including the action act that leads to K+1, and previous frames. It can't peek into the future it's trying to predict. Makes sense. Okay, so now they have this model, V-JEPA2AC. It can predict the representation of the next state, given the current state, and a proposed action. How do you turn that capability into the robot actually performing a task, like picking up a block?
That's where model predictive control, or MPC, comes into play. It's a common technique in robotics control. Given a goal, which in this case is provided as a goal image, showing what the desired final state looks like, and the robot's current state from the camera, the system plans a sequence of actions over a short, fixed time horizon, let's say T steps.
Okay, plans a short sequence.
Right. Then, it executes only the first action from that planned sequence. After executing that action, it observes the new state of the world through the camera, gets the new representation, and immediately replans from that new state for the next T steps. So it's constantly correcting itself based on reality.
Exactly. This continuous feedback loop, plan, act, observe, replan, helps correct for any errors in the model's predictions or unexpected changes in the environment.
And the core of this planning, you said, is essentially searching for the best action sequence. How do they define best here? What's the objective?
Best means finding an action sequence that minimizes a specific goal-conditioned energy function. They define this in equation 5. What they're minimizing is basically the difference, specifically the L1 distance between the world model's imagined state representation T, steps into the future, assuming it took a particular sequence of actions, and the representation of the goal image. Both representations, the predicted future and the goal, are generated by the same frozen V-JEPA2 encoder.
Okay, so let me see if I get this. The model is essentially saying, if I do these actions, what representation will I end up in? How close is that representation to the representation of the image showing my goal? It's trying to close the gap in representation space, like in Figure 7.
Precisely. It's searching for an action trajectory that makes the predicted future state representation as close as possible to the goal state representation in the latent space. It's finding the path of actions that connects the current state representation to the goal state representation within its internal learned world model.
Very cool. And how does it actually find that optimal action sequence? What's the optimization method?
They use a method called the cross-entropy method, or CEM.
CEM. How does that work in this context?
It's an iterative optimization process. You start by sampling a batch of possible action sequences, essentially, random guesses at what the robot might do over the next T steps. These samples are often drawn from a simple distribution, like a Gaussian.
Okay, lots of random plans.
Yeah, maybe like 800 of them per planning step in their case. Then you evaluate each of these sampled sequences using that energy function we just talked about. How well does each sequence get the model's predicted future representation towards the goal representation?
Rank them by how good they are.
Right. Based on that ranking, you select the top K best performing sequences, the ones that minimize the energy the most. You then use these top sequences to update the parameters of your sampling distribution, typically the mean and variance of the Gaussian, so that the next batch of samples you draw is more likely to be in the region of the action space that yielded good results.
So it focuses the search over iterations.
Exactly. You repeat this sampling, evaluating, and refining process for several iterations. The mean of the final refined Gaussian distribution over action sequences is then chosen as the action trajectory to execute, well, the first step of it.
And they mentioned adding a constraint to the actions, limiting how much the robot's end effector could move in a single step.
Yes, that's right. They constrained the actions to lie within an L1 ball, which effectively limited the single-step displacement of the robot's end effector to about 13 centimeters. This is a pretty practical constraint, partly because very large, rapid movements might be outside the distribution of the droid teleoperation data the model was trained on.
Right, out-of-distribution actions can be risky.
Yeah, and it also helps ensure smoother, more predictable, and probably safer robot behavior.
Okay, now one of the most exciting parts is the actual robot deployment. How did V-JEPA 2AC perform when they put it on real robots?
This is a really key result from Section 4.1. They deployed the trained V-JEPA 2AC models zero-shot.
Zero-shot meaning?
Meaning the model was trained once using the droid dataset and then used directly, without any further fine-tuning or adaptation, on physical Franco robot arms located in different labs that were not part of the original droid dataset collection.
Wow, okay. And they used a pretty challenging camera setup too, right? Not some fancy calibrated stereo system.
Absolutely not. They used an uncalibrated, low-resolution monocular RGB camera. That's just a single regular camera feed without precise depth measurements or calibration markers. This kind of setup is notoriously difficult for many traditional robot vision and control approaches.
And the same model weights worked across different physical robots.
Yes, the same model weights and the same inference code were used across different robots, which really highlights the generalization capability learned by the model. They use blocking control, meaning the robot waits for one action command to finish before accepting the next.
Okay, let's get to the results then. How did it actually do on the tasks they set up?
So first, they tested relatively simple single goal reaching tasks. The robot just has to move its end effector, its hand, to a target location that's indicated by a goal image. This really tests the model's basic action understanding and its ability to interpret 3D space, including depth, just from that single simple camera view.
And the performance. You mentioned figure 8.
Performance was pretty impressive. They consistently achieved high accuracy, with the robot's end effector ending up less than 4 centimeters away from the target location on average. And importantly, they showed that the robot's error typically decreased monotonically over the steps of the task.
Meaning it consistently got closer and closer.
Exactly. It shows the planning system, guided by the world model, was effectively steering the robot towards the goal. This is similar in outcome to classical visual servoing techniques, but crucially, V-JEPA 2AC achieved this by learning from unlabeled real-world video and a bit of PELIOP data, not through explicit geometric programming or painstaking calibration.
That's a big difference. They also tackled more complex tasks, didn't they? Like prehensile manipulation, actually grasping and moving objects.
Yes, they moved on to tasks like picking up an object, moving it while holding it, and full pick-and-place sequences, which are much harder. They show some results in Figure 10 and Table 3 for the pick-and-place task, which is quite challenging.
Needs precision.
Definitely. They actually use multiple sub-goals to guide the robot. So instead of just showing the final placed object, they give it intermediate goal images. Maybe first a goal image to grasp the object, then one to move the grasped object to a position near the final target, and then finally a goal image for the actual placement. They show this sequence in Figure 14 in the appendix.
Breaking the problem down.
Exactly.
Yeah.
These tasks require much more sophisticated visual control and intuitive understanding of physics. Don't drop the object midair, and the ability to compose these different skills together.
And how did V-JEPA 2AC compare to other methods on these harder tasks, particularly maybe generative models? They compared it to Cosmos, right?
Yes, this comparison in Table 3 is really critical. They compared V-JEPA 2AC, which predicts representations, directly against Cosmos, which is a state-of-the-art action-conditioned video generation model. Both models use the same planning method, CEM, and were run on the exact same hardware, a single RTX 4090 GPU, for fair comparison.
And the results.
The difference in planning efficiency was just stark. To compute the action sequence for a single step of the robot, Cosmos took a full 4 minutes.
4 minutes per step. That's very slow for real-time control.
Extremely slow. In contrast, V-JEPA 2AC, running on the same hardware for the same task, took only 16 seconds per planning step. And get this, V-JEPA 2AC achieved this speed while using 10 times more samples in its CEM search process. So it's doing a much more thorough search much faster.
Wow. So dramatically faster planning. How about the success rates? Did the faster planning come at the cost of performance?
Quite the opposite, actually.
Yeah.
Despite being vastly faster at planning, V-JEPA 2AC achieved significantly higher success rates across all the complex manipulation tasks they tested compared to Cosmos. Cosmos performed reasonably well on the simple reaching tasks, but it struggled much more when it came to interacting with objects, like grasping and placing.
And they noted Cosmos needed extra tuning.
Yeah, the paper mentions they had to perform quite a bit of tuning on Cosmos, adjusting things like learning rate, dropout, noise levels, just to get it to work reasonably well in this action-conditioned planning setup. These were adjustments away from its default settings used for pure video generation, suggesting it wasn't inherently well-suited for this control task, unlike V-JEPA 2AC, which seemed to work more out of the box.
This comparison seems to strongly support the paper's core hypothesis, doesn't it? That predicting representations is potentially much better suited for efficient and effective planning than trying to predict or generate visually perfect future pixels.
It really does. Generating those high-fidelity future frames is computationally very expensive, and it seems less effective for capturing the precise state changes and dynamics needed for robust control compared to predicting directly in this lower-dimensional, dynamics-focused latent space learned by V-JEPA.
Seems like it cuts through the visual clutter.
Exactly. Focuses on the information most relevant to how the world behaves and how actions change it. However, it's not perfect. Like most world models based on autoregressive prediction, the paper does acknowledge a limitation in planning for very long horizons, mentioned in section 4.4. When you predict step by step by step, small errors can accumulate over time.
Right, the prediction gets fuzzier the further out you go.
Yes, so the accuracy of the predicted future state tends to degrade the further out you try to plan. It's a known challenge for these kinds of models.
And just to help understand what the model is predicting in its internal representation space, since we can't directly see representations, they trained a separate decoder to visualize things. Appendix B.3, Figure 15.
Yes, exactly. Since the representations themselves aren't pixels, they trained a simple feed-forward network, another VIT in this case, to map the V-JEPA2 representations back to image pixels. By applying this decoder to the outputs of the V-JEPA2AC predictor, those predicted future representations for a given action sequence, they could generate visualizations of the imagined future states.
So you can kind of see what the model thinks will happen.
Sort of, yeah. Figure 15 shows some examples. You see the robot's actual observation, maybe a reconstruction from the V-JEPA2 encoder itself, just to check visual fidelity, and then the rollout visualization from V-JEPA2AC's predictions. This visualization capability is really key, not just for debugging, but for understanding what the model has actually learned about dynamics and how it perceives the consequences of its planned actions.
Okay, that covers the robotic side. Moving beyond robot control, how capable are the raw representations learned by the base V-JEPA2 model for more general visual understanding and prediction tasks? Section 5 looks at this.
Right, they wanted to see how good the features learned just from observation were on their own. They evaluated the frozen V-JEPA2 encoder's representations on a range of standard video understanding benchmarks. The standard way to do this is to train a small, simple network, often called an attentive probe, or a linear probe, on top of the frozen encoder's output features for a specific downstream task.
So you're just using the encoder as a fixed feature extractor.
Exactly. It tests the quality of the pre-trained representations themselves.
And they tested it on a suite of 6 classification tasks covering different aspects. Appendix C has the details.
Yeah, a good mix. They included benchmarks specifically designed to test motion understanding, like something something V2, SSV2, and diving 48, which require understanding temporal dynamics and object interactions. And they also included tasks that rely more on general understanding or appearance-based features, like gesture, hand gestures, Kinetics 400 general actions, Koyan instructional steps, and even ImageNet, still image classification.
And the results were pretty strong across the board. Table 4 shows this.
Very strong. The large V-JEPA2 VITG model achieved state-of-the-art performance on the challenging motion understanding tasks, significantly outperforming previous leading models designed specifically for video, like intern video. For example, on SSV2 and Diving 48, VGP2 set new records.
That's impressive for a model not explicitly trained for action classification.
It really is. And it was also highly competitive on the appearance-based tasks like ImageNet, even though it was trained only on video. Overall, it achieved the best average performance across all 6 benchmarks, which demonstrates that its observationally learned representations are genuinely general and powerful for diverse video understanding tasks. And using the even higher resolution VITG 384 version improved performance further still.
Okay, strong on classification. They also looked specifically at human action anticipation in Section 6, predicting what a person's about to do just from watching a short clip leading up to the action. Appendix D has the details here.
Yes, this is a fascinating task. They use the Epic Kitchens 100 dataset, or EK100. This dataset consists of egocentric videos recorded from a person's point of view of people performing everyday activities in kitchens. The specific task is to predict the future action, which is defined as a verb plus a noun pair, like open cabinet or wash plate, up to a second before the action actually happens in the video.
That sounds hard. How do they measure performance?
They use a metric called mean class recall at 5. This is well suited for EK100 because there are often multiple plausible future actions a person could take, and the distribution of actions is very long-tailed. Some actions are common, many are rare. Recall at 5 checks if the correct action is within the model's top 5 predictions and averages across classes to handle the imbalance.
Right. And VGP2 did well here too, Table 5.
Impressively well. They saw a very clear trend. The action anticipation performance scaled almost linearly with the size of the V-JEPA encoder, going from the 300 million parameter VITL model to the 1 billion parameter VITG model resulted in a substantial gain of over 5 points in recall accuracy.
So bigger models predict actions better.
Seems so. And adding the higher input resolution with VITG 384 boosted it even further by almost another 2 points. What's particularly notable here is the comparison to prior state-of-the-art. V-JEPA2, which was purely pre-trained on unlabeled video and then just had a small probe trained on top for this task, significantly outperformed the previous best method, called PlausiVL.
How much better?
PlausiVL actually used a very large language model, 8 billion parameters, specifically designed for this kind of plausible future prediction. Yet V-JEPA2 VIT 384 achieved a 44% relative improvement over PlausiVL's reported score, despite having far fewer parameters overall. They show some nice visualizations of successful predictions in Figure 11, too.
Wow, that's a huge margin. It really suggests that a deep, implicit understanding of visual dynamics learned from pure observation is an incredibly strong foundation for predicting actions, maybe even better than approaches relying heavily on language models for the specific task.
It certainly points in that direction. The ability to model the underlying physical and intentional dynamics seems key. However, they are careful to point out the limitations, too, in Section 6.1. While the performance on EK100 is high, it's not perfect. Figure 18 shows there are still failure cases where the predicted verb or noun, or both, are wrong.
And prediction gets harder further out.
Yeah, as you'd expect. And as Figure 18 also shows, the prediction accuracy naturally degrades the further into the future you try to anticipate the action. Plus, you have to remember the limitations of the dataset itself. EK100 is confined to kitchen environments and a predefined, fixed set of action categories. So generalizing this performance to totally new actions or drastically different environments isn't guaranteed based solely on this benchmark result.
Good caveats. Okay, one last major area they explored. Can these powerful, purely visual representations learned by V-JEPA2 be effectively used for open language tasks, like answering natural language questions about videos? Section 7 covers this.
Yes, and this is super interesting because VGP2 itself has seen zero language during its pre-training. The answer is yes, but it requires explicitly aligning the visual representations with a large language model, an LLM.
How do they do that alignment? Appendix E has details.
The general approach is to build a multimodal large language model, or MLLM. You take the frozen, or sometimes fine-tuned, VGP2 encoder as your visual backbone. Then you need a way to bridge the gap between the visual features and the language model's input space. They use a small projector network, typically a simple multi-layer perceptron, MLP, to translate the V-JEPA2's patch embeddings or visual tokens into a format that the chosen LLM can understand and process alongside its normal text embeddings.
Okay, so a translation layer. And how do they train this combined MLLM system?
They train it on a very large data set of image and video text pairs. They scaled this up significantly, eventually using up to 88.5 million paired examples. This alignment training often happens in stages, maybe starting with image captioning and image question answering to get the basic vision language grounding, then moving on to video captioning and video QA tasks.
And image data is important even for video tasks.
They found that including large amounts of image text pairs was actually crucial for achieving high performance on the video question answering tasks. It seems to provide a strong foundation. During this alignment phase, the V-JEPA2 visual encoder can either be kept completely frozen, just using its pre-trained features, or can be fine-tuned end-to-end along with the projector and parts of the LLM.
And they evaluated this MLM setup on a whole battery of video question answering benchmarks.
Right, a diverse set. Tasks designed to test different capabilities, things like understanding memory, abstraction, intuitive physics from video, like perception test MVP, understanding temporal relationships, temp compass, temporal bench, tomato, as well as more general video understanding benchmarks, MV bench, PV bench.
And crucially, they did a controlled comparison first, right, to isolate the effect of the V-JEPA2 encoder itself, section 7.2, table 6.
Yes, this comparison is very telling. They set up a controlled experiment, same moderate-sized alignment dataset, 18 million pairs, same LLM, Qwen2 7B instruct. They compared V-JEPA2, used as a frozen encoder, against several other leading image encoders like Dano V2 and Cyclip2, also used frozen.
And the key finding?
The key finding was that V-JEPA2, despite being pre-trained purely visually with absolutely no language supervision during its initial learning phase, achieved competitive performance on these open-ended video question answering tasks compared to these other very strong image encoders, many of which were pre-trained using objectives that involved language or text in some way.
That's actually a huge deal, isn't it? It implies that the rich visual understanding and the implicit world model learned through just self-supervised video prediction provide a foundation of semantic knowledge that's robust enough to support complex language tasks just by being aligned with text later on. It didn't need language during the visual learning part.
Absolutely. It's strong validation for the power of the self-supervised visual pre-training approach itself. It suggests the model learned something genuinely meaningful about the world, not just superficial patterns.
And they also showed that scaling helped here too, section 7.3, table 7.
Yes, consistent with the other tasks, they showed that scaling the V-JEPA2 encoder size from the 300M VITL to the 1B VITG, and also increasing the input image resolution from 256 pixels up to 512 pixels during the end-to-end MLLM training consistently improved the VidQA performance. This mirrors findings in image VQA and suggests there's still potential benefit from further scaling the vision component.
But the biggest leap in VidQA performance came from something else, section 7.4.
Right. The biggest single factor for pushing VidQA performance to state-of-the-art levels was scaling the alignment data. When they trained their largest V-JEPA2 model, VITG384, with a more capable LLM, specifically Llama 3.18b, using their full, massive 88.5 million image and video text pair dataset.
Then they hit SOTA.
Then they achieved state-of-the-art results on multiple challenging VidQA benchmarks, including perception tests, MVP, temp compass, temporal bench, and tomato. This provides really strong evidence that a high-quality visual encoder pre-trained entirely without language supervision can indeed reach peak performance on demanding language-based video understanding tasks if it's subsequently aligned with a sufficiently large and diverse set of multimodal data.
Fascinating. So, okay, let's try to put V-JEPA2 in context now. Based on everything we've discussed, where does this work fit within the broader landscape of AI research? Section 8 touches on related work.
Well, as we mentioned, the idea of world models for planning isn't new. It has a long history in AI and robotics. But making them work effectively and efficiently for real-world robot control directly from raw, high-dimensional video input like this has remained a significant challenge. V-JEPA 2AC really makes strides on that front.
And as we saw with the Cosmos comparison, it clearly distinguishes itself from recent action-conditioned video generation models.
Exactly. It demonstrates superior planning capabilities and much greater efficiency by focusing on predicting essential state changes in a learned latent space, rather than getting bogged down in generating photorealistic future pixels.
It also seems different from some of the recent vision language action models, or VLAs, for robotics.
Yes. It contrasts with many VLA models that often rely heavily on imitation learning. They typically require large data sets of successful, expertly collected robot demonstrations to learn control policies directly. V-JEPA 2AC, on the other hand, uses model predictive control, which can potentially learn from a wider variety of interaction data, maybe even failures or suboptimal attempts, not just perfect executions, and it relies heavily on planning at inference time, which gives a different kind of flexibility and adaptability compared to purely learned imitation policies.
So ultimately, VJP2 positions itself as a powerful vision foundation model, but one learned purely from self-supervised video observation. It shows that this kind of large-scale observational learning can create generalist visual encoders that go beyond just understanding videos or answering questions about them.
Right, extending that understanding to enable effective physical interaction and even zero-shot planning in completely new environments. It's a compelling demonstration of the potential of learning these rich, predictive world models primarily from the vast amounts of passive observational data that are readily available.
Okay, let's bring it all back then and recap the core takeaways from this deep dive into VJP2. What are the absolute key messages?
I think first and foremost, VGP2 successfully demonstrates that you can learn a powerful internal world model and incredibly rich visual representations primarily by observing web-scale video. It does this using the JP principle predicting in a learned representation space, not pixels. And it leverages only a small amount of robot interaction data later on just to condition this learned model on the effects of actions.
Second, the representations learned this way are genuinely effective on their own. They achieve state-of-the-art performance on challenging visual tasks, like fine-grained motion understanding and anticipating future human actions, outperforming previous specialized models.
Third, even though these visual representations are learned without any exposure to language, they could be successfully aligned with large language models. And when aligned using sufficient language-paired data, they enable state-of-the-art video question-answering capabilities. The visual foundation is strong enough.
And perhaps most excitingly, certainly for the embodied AI folks, the VGP2AC model, built on these learned representations and trained with that limited interaction data, enables successful zero-shot execution of complex object manipulation tasks on real robots. It does this using model predictive control, and it's significantly faster and more successful at planning for these tasks compared to comparable generative model baselines.
Yeah, putting it all together, this work really represents a significant step forward on the path towards creating AI systems that don't just passively see the world, but can genuinely understand its underlying dynamics, predict how it's likely to change, and then act within it effectively and efficiently.
So what does this all mean for you, listening? Think about an AI that builds this deep, almost intuitive understanding of how the physical world works, mostly just by watching millions of hours of videos absorbing knowledge about everything from object physics and collisions to typical human behaviors and interactions.
And then, with just a little bit of direct experience, not necessarily perfect, labeled expert demonstrations, but maybe just any data showing how its own actions influence the world, it can leverage that vast learned understanding to figure out how to perform new tasks, even manipulate objects it hasn't encountered before in entirely new situations.
This potential paradigm shift, moving away from needing massive amounts of task-specific, highly curated interaction data or needing to generate pixel-perfect simulations, and instead leveraging readily available observational data to learn predictable dynamics in an abstract, latent space. Well, that raises a really important question for the future. Just how far can this approach of learning by watching, combined with minimal targeted interaction, actually take us towards building truly generalist, adaptable, embodied AI systems that can learn and operate effectively in the messy, complex, unpredictable real world?
Something to definitely mull over.
Indeed, something to think about until our next deep dive.